There is only one rule in system design. There is no perfect solution. It will always be a trade-off for something you really need with something that is less important. In our previous video of scaling, we have seen the backbone of distributed systems, which is load balancer. We were only able to scale our application horizontally due to this component. So today we are going to learn everything about load balancers. Let us first understand why do we really need load balancers. In today's digital world, the stability and performance of the web application is most important. Imagine that millions of users are trying to access your service simultaneously. Now, without an efficient system in place, your service could easily become overwhelmed. That can lead to either slow response times or even system crashes. This is where load balancer comes into play. It ensures that the traffic is distributed evenly across the servers so that no single server is overburdened with the requests. A load balancer is a tool which can be a network device or a software that helps distributing incoming network traffic across many servers. But wait, how something can be a device and a software also? Let us understand this. A hardware load balancer is a physical device that can be placed inside your network infrastructure. These devices are designed to be very efficient at distributing high traffic, typically in the large data centers. On the other hand, a software load balancer is a program that runs on a standard server. It performs the same traffic distribution task but can be more flexible and cost effective. But why do we have two different kind of load balancers for the same work? They mainly differ in their use cases where traffic volume and flexibility is the key. Hardware load balancers are suitable for large data centers where high performance and security is critical. Software load balancers, on the other hand, are ideal for small to medium sized businesses where cost effectiveness and flexibility are more important. They can be easily scaled and adapted to the changing requirements too. Let us understand where exactly the load balancers are present in actual infrastructure. This is going to be a flashback to college days. So if you are not really interested in computer networking part, you can skip to the next chapter from bottom. But I request you to not skip it because if you are going to learn how to design a system, then you should know the hows and whys of the system components. So let's get into it. During our college days, while learning about computer networks, we might have come across a term called OSI model. Don't worry, we are not going to learn that whole 7-layer Burj Khalifa again. Let us just briefly understand about the model. We will see the layers at which the load balancers are placed and why it is placed under there only and not on any other layer. OSI model is a conceptual framework which is used to understand and implement network protocols in 7 layers. Each layer has a specific function and it can communicate with the layers directly above and below it. It starts with the physical layer, which is completely hardware driven, all the way up to application layer, which is completely software driven. The OSI model helps us understand how different networking protocols interact and work together. You can let me know if you want me to cover the complete OSI model. I'll have a dedicated video on that also. Because it's always better to know how the things are working under the hood. Now coming back to load balancers. They are commonly placed at layer 4, which is transport layer, and layer 7, which is application layer. When a load balancer is placed at layer 4, it manages the incoming traffic based on IP address and port numbers. It will not inspect the content of the message. It makes decision based on the network information available in transport layer. Because load balancer at layer 4 operates using basic information about the source and destination, that makes it faster and less complex to implement. Due to this, it can handle higher volume of traffic with a very low latency. So the main benefit we get by placing a load balancer at layer 4 are high performance and simple implementation. But placing load balancer at layer 4 will not be able to cover the vast requirement of our real world. In the real world scenarios, we may need to distribute the traffic based on user data like user ID, location of the user, etc. And because load balancer at level 4 cannot make decision based on such data, that makes it more rigid with less control and less flexibility. So to have more control and flexibility, load balancers are also placed at layer 7, which is application layer. Layer 7 load balancers manage traffic based on the application level data such as HTTP headers, cookies, and URL paths. They inspect the content of messages to make more informed routing decisions. Layer 7 load balancer provides so much flexibility and control, but it adds up to its complexity. So you need to choose based on your system requirements. Now the question is, why only layer 4 and 7? Why not any other layer to place the load balancers? Because these two layers provide the necessary network and application level information to properly manage the load distribution. Other layers do not provide that necessary data that is required to make an informed decision on routing the request to appropriate target. The more we dig deeper in the computer networks, the more we will be pulled inside. So let's just get out of this computer network mess and go to our simple yet complicated world of system design. So now we know where exactly the load balancers are placed in network infrastructure. So we have multiple servers. We wanted to distribute the traffic to those servers. For that, we put in a load balancer in between. Load is getting distributed. Everyone is happy. But how come the load balancer knows which request to send to which server? That configuration we can define in the load balancers. There are different ways, or we can say load balancing algorithms, for distributing incoming traffic across multiple servers. Let us see what are these algorithms. The first one is round robin algorithm. This is one of the simplest load balancing algorithm. It distributes incoming requests sequentially and evenly across all the servers. Suppose there are 10 requests received by the load balancer, which is using round robin algorithm to distribute the requests. And we have 5 servers under this load balancer. So it will send the first request to first server, second request to second server, like this till the fifth request to fifth server. Now there are no more extra servers left, but we have more requests from customers. So under round robin algorithm, the load balancer will again start from the first server by sending 6 requests and 7 requests to first, second and third servers. So like this, it will evenly distribute the load on all the servers. So no server will be overwhelmed. This method is effective for servers with similar specification and when session persistence is not required. The next algorithm is least connection algorithm. In this, traffic is directed to the server with least number of active connections. This approach is more dynamic than the round robin because it considers the current load on each server and then route the requests. This approach is useful when different tasks consume different amounts of server resources. It will ensure that no single server gets overwhelmed. Similar to this approach, there is one more algorithm which focuses on least response time. The requests are routed to the server with least response time. Moving to the next algorithm, suppose you need a load balancer which can route a request from single user to the same server every time. Or maybe you just want to maintain user session in the server. For that, we have another algorithm which is IP hash method. It takes the IP address of the client and then apply a hash function on that. By calculating the hash of IP address and dividing it by total number of servers, this method consistently redirects a user to the same server. That sounds familiar, right? It is similar to how the hash map works. Now, remember the round robin algorithm? By the way, which is amazing because it evenly distributes the load. But suppose your servers are not of the same capacity. Servers are of different configuration, different RAM, CPU, disk space. Let us say your first server can take maximum 2 requests, but your second server can take up to 10 requests easily because it has more resources available. So in such scenarios, do you think the simple round robin is sufficient enough? It will strangle the first server up to its maximum, but will underutilize the second server, which can actually take up more requests. So what could be the solution to this? The solution to this is weighted round robin algorithm. In this, we assign a weight to each server based on their capacity. Servers with the higher capacities will get the larger share of the requests. Now, similar to the weighted round robin, the weighted least connection algorithm also assign a weight to each server. Only difference is it does not route the traffic based on the sequential order but focus on the number of connections and the server's capacity. Servers with higher weight will handle more connections than those with the lesser weight. Now moving to the next algorithm, suppose your application is worldwide and you want that if a user from United States tries to access your application, then you want that request to route to the server either in United States or any other nearest location to the user. For such requirement, load balancers can use geographic load balancing algorithm. It distributes the request based on geographical location of the client that aim to connect the user to the server nearest to them. This reduces the latency and improves the load time. These were all the good things about load balancers. But if you remember what I said in the beginning, there is only one rule in system design. There is no perfect solution. Just like any other solution, load balancers also come with some problems, or we can say limitations. There are few problems with load balancers that we need to consider before adding them into our systems. First one is they create a single point failure. Although from the server side, they also help us minimizing the single point failure by redirecting the traffic to the healthy servers in case any server crashes. But what will happen when the load balancer itself is down? This will create a single point failure in the system. Another issue is regarding capacity of the load balancer. It is just another machine which can have a finite resources, thus can serve a finite number of requests. When business grows, the number of requests will also be increased, which will clog or overload the load balancer and impact the overall system performance. So now it's a question for you who are watching this video. Tell me what are the solutions we can think of to overcome these limitations in load balancers. We will discuss the most appropriate solution given in the comments in our next video. Now, this concludes our load balancer session. Load balancer is very important component in any scalable system. So that's why we have to understand how it works. So if in today's video, if you have learned something, don't forget to give us a thumbs up. Also subscribe to the channel and press the bell icon. Once again, thank you so much for watching. I'll see you in the next video. Till then, keep learning.